Back at it again, man. The peoples. Back at it again. I am pulling up the information for the AVL stream. AVL trees, guys. What day was that? What's today? I feel like it's been like multiple days. 3 days ago we were doing binary trees. Yo, Martin, thank you for joining. So today we're gonna be doing AVL. I know I kind of did this a little backwards. Because the binary tree is more confusing than the AVL. But I wanted to jump on binary trees a few days ago because I thought I was gonna get stuck. But turns out I've been doing this so long that it's no longer as hard as I thought it was going to be. Not saying it's easy, but I am feeling a little bit more confident. I do need to go back and figure out a few things that I was a little bit maybe stuck on with the binary tree. Primarily removing nodes. But that's about it. That was the only thing I was stuck on, I think. Right? Or am I mistaken here? Let me open my Xcode really quick. And by the way, guys, excuse me if I'm a little bit out of it. Hardly got any sleep last night. I'm gonna keep it honest with y'all. So let's see here. Okay, so binary tree. Last time I was stuck on the remove method. Let me just go over some of these methods really quick. I almost feel like maybe I should rewrite the binary search, but it's like, why even do that, right? I binary search, I understood it. Merge sort, I understood it. So I think we can progress. Yo, content says being a black content creator is hard, man. Scott's so funny, bruh. Oh, did you watch the video? Did you see how many comments that one got? I haven't even looked and seen. I know last time I checked it, I had a decent amount of comments though. So to make the binary tree, before we made a tree node, we made a value of left and right, left node, right node. We made an initializer that had a parameter of an integer. Then we have the binary search tree actual class that has the root, which is just the first node, which we can call it root. We can call it first node. Usually people call it root, but it doesn't really matter. Then we had an insert algorithm. Now, the Java example that I saw, he was using helpers. And I think, honestly, using a helper makes it easier to understand than if I was just trying to do the work inside of the algorithm itself. In fact, when I was at the hospital, I had my other computer with me. And in my old computer, I had an example of a binary search tree, and I did it differently. I did it using a while loop, and it was extremely confusing. It was extremely confusing. So I think that this is probably a better way of doing it, right? You have the insert method. You check to see if the root is nil. If the root is nil, you make the root node of the binary search tree the new node, and you return that node, right? But you have to remember that you need to assign it before you return the node. Then, if it's not nil, if the base root node is not nil, you have an insert helper. You have the insert helper. The base node is the base node that's getting passed in. And then the new node, right? And since this is a recursionary function, you have root left, root right, right? You check in here, because remember, we're calling this function multiple times. So you're going to check in here to see if the base node is nil. If it's nil, we just return the node that you just passed in. Yeah. You return the node that you just passed in, right? Because you're assigning that value to the root left and the root right. So while we're looping through every single node, When you get to a node where there's no value, right? Let's say it was less than the value we're checking, root.left is nil. Now, when you do this, you're going to assign, right? You're going to assign the value to root.left because that's what you passed in as the base node. Now, the thing is, there's multiple ways to do this, but this was, in my opinion, this is like the simplest way to do it. Then he has the recursionary helper. He has recursionary helper, and it was very simple to just go through each item, right? So we check to see if the left node is nil. If it's not nil, then we call the recursion function on the left, and we do the same thing for the right. And then we just print the value of each node that's getting called in between these two functions. And depending on how you line this up, it will call it differently. So we can call it here, or we can group these two functions together and call it underneath. I don't know if they're gonna make us do any binary search trees, but it doesn't really matter. So then we had a search method, and it's search for a tree. We pass in the root, we pass in the value we're searching for. We check to see if the root is nil. If the root is nil, we return false because it obviously means the tree is empty. Otherwise, we loop through everything, right? So we say if the node is equal to the value that we're looking for, then return that node, right? And while we're doing this, we have return functions for both the left side, okay, and the right side. If the node.value is less than the key, right? So the key is here and the value of the node is less than the key, then we know that we need to wait. See, this is why I like using key less than instead of it being this way. Node.value is less than the key. So that means the key is greater than the value of the current node, which means that the key is on the right side, right? Because right is going to be positive, left is going to be negative. So then we're just going to go back and we're going to assign the base node to be node.right of the node that we passed in. And we're going to continue the recursionary function. And we're just going to do that until we find the value. When we find the value, then we're going to return it. If we don't find the value, we're going to keep going deeper and deeper and deeper and deeper. Yo, Shouty T, thank you for joining the stream. He says, yo, congrats on the baby. Thank you, man. So the spot where I was confused, guys, was with the remove function. So with the remove function, the first thing I tried to do was I tried to call the search function to confirm that the key actually existed, right? So we have this logic. If search for key dot state, this is going to return a Boolean value of true or false. If it's true, it means that we know that the binary tree has the value we're searching for in it. And this is obviously O(n) log, big O notation time, because we're splitting the tree down the middle when we're searching for it. You know, I could have just done this whole function over again, but I think that it's more efficient if we just reuse the methods that we already have. And then we have the helper method, which is remove helper, right? And then we pass in the key we're searching for, and we pass in the base node. The first time you do the remove, the base node is going to be the root, right? And then we go in base node equals node, which I'm thinking, do I need to do this logic here? Base node equals node. Are we changing the value of node at all? We're not. So this here, I don't even know if I need to change this to node. What we're doing here is we're passing in the value we want to delete, right? And we're passing in the base node. And we're saying if node.value equals key, we're going to return nil, right? And then here, we're going to check node.value is less than the key. If it's less than the key, we know we're going to go to the right. If it's greater than the key, we're going to go to the left. We're going to call the recursionary function over again. We're assigning the value of remove helper to the right node. So remember that if we pass in a node and that node's value contains the one we're looking for, then we're going to go ahead and we're going to remove it from here. But remember that for each one of these node.right, right? Node.right, we're passing in node.right. Node.right is now going to be the node.value. So it's going to return nil, and that's going to assign, that's going to, when it bubbles back up to the top, because remember, this is a recursion. So we're going down the tunnel. When it bubbles back up to the top, it will automatically assign that nil to node.right. And then we're returning node. So let's run this really quick one time here. It's running. And if you remember last time when we were running this, I was having an issue removing the value from the binary tree. But I think that the reason I was having that issue was because we were not assigning anything to the node.left and node.right in the recursionary function. See how it did remove it? Now there is a problem here, and I said it in the comments. Works for all except first node. So we have an edge case. If the first node is the node that we're looking for, which in this case is 15, then we are unable to remove it. Why? Let's find out why. So we're passing in 15 as the node, right? Let's run it again. And yet 15 is still in the list. Why is 15 still in the list? Let's think through this. So we check to see if 15 exists in the list. It does, right? And we can verify this by doing a print here, right? Actually, we don't even need to do that. Value item to delete, value found. We already have the logic. Value found, item item to delete. Okay, so we passed in 15, right? The first node, the base node. This node is 15, return nil. So why does it not do anything? It's the very first node. Why does it not do anything? When we're looping through the tree, there's no way to verify if the node has a parent node, because we never assign a parent node to any of the nodes. 15 is the first node in the list. We're telling this to return nil, right? So it returns nil, but then it doesn't matter if it returns nil because it doesn't assign anything to the remaining. It doesn't assign anything to the remaining items in the tree. How would we be able to tell if it's the first node in the list? You know how? I'll tell you how. In here, we already know what the root is. See? So we could say something like if node dot, we don't need to do it. If node equals, I think if we do a triple equal sign, we'll be able to confirm if it's the root node or not. Root. We can do this. I'm trying to remember. The triple equal sign means that they're the same instance of the same class, or does it just mean that they're the same class type? I don't remember. So we're gonna make a print statement here. Print same instance. And if we see this happen, he says, hi, bro. Missed you guys. Abdul Kamara, thank you for joining, bro. Let's just run this and see what happens. Let's see if it prints out same instance or if it doesn't. Okay, same instance, it does. What happens if... Let's change the value to a different number in the list. So let's change it to 86 since we know 86 is in this binary tree. 86. Let's run it again. Let's see if it says, okay, so it doesn't. Value item to delete, value found. It doesn't. Okay, so this does confirm. There's no way for me to... So triple equal sign does confirm if they're the same instance of a class, which is basically just saying that this node instance is equal to the exact same instance of the root. So we do have a way of confirming that it's the first item in the list. So now what I want to do, we're just going to erase the entire tree, right? Or actually, let's do something different. Let's be smart here. Let's be clever. So if it is the root, then we're going to say root equals, and we're going to assign the next higher value of, we're going to assign the next higher value of the tree as the root. So I think what I would like to do here is node dot left, right? But then we run into another edge case. If we make the node dot left, the new root, everything that was on the right is going to be lost, right? So we need to do root dot, and actually this is it should be right, not left. Sorry. So root dot left is going to be equal to, let's think here. Node dot left is what you'd think. But what we really want to do is add. Let's just add the values back in. So let's just go insert, and let's insert node dot left, which would be easier than doing what we were trying to do. We can make an if let statement here, or a guard, right? If let left node equals node dot left, do this. And then in here, we could have done this on both of them, to be honest. In here, we can grab this and we can go left node right here. I think this should work. And let's just see if we continue having all of the values. So what we did here is we made the root node.right. So we got rid of 15. We got the next highest value. We made that the root. The items that were attached to the original root, we have them stored in node.left because we're comparing the node already. So we don't need to keep a reference to it. The first node that was on the left, we have an instance of that node. We're inserting it back into the tree. it should go through and compare it to the highest value, the next lowest value, and we should be able to get through the entire tree again. So let's try this. Okay, so that worked. He says, hella Tesla bots will be roofing within 5 years. Yo, random stuff. Thank you for joining. Chemo Shadowbanation. Have you considered the wonderful world of construction? Oh no, dude. Do I look like a construction worker? He says, wait, I come into being a black content creator is hard. Now what? As a white man, I'm supposed to think other than I'm not welcome here. How so, bro? How is that your takeaway, Chemo? My point with that video is that it's very hard to not be a stereotype, but we can get into it in the afternoon when I stream in the afternoon. For now, I'm just studying. This looks like it worked though. This looked like it worked. So we have the first item of this list is supposed to be 15. And if you can look at the list now, you can see we have 12, 13, 15, 24, 63, 77, 86, 97. There's a total of 1, 2, 3, 4, 5, 6, 7, 8 items in this list, right? And now we have, there should be 7 items. 1, 2, 3, 4, 5, 6, 7, 12, 13, 24, 63, 77, 86, 97. We essentially reorganized this. We reorganized this list so that it would remove the first node. We're removing the first node. We're making the root node the next highest value. We're grabbing the left node and we're inserting the left node with all of its attached elements. And we can even add let's add a new value to this list. Let's add 2 and let's add 5. And let's run it again so we can see that we'll still have all of the low numbers as well. Run it again. So now the list is updated and we have 2, 5, 12, 13, 15, 24, 63, 77, 86, 97. And if you go down to the list, we still have the 2, we still have the 5, we have 12, 13. The only number that's missing is 15, which was the root number. And that was because we used the triple identifier to determine if the root node is equal to the node that we're on. And just to make sure that I'm not misremembering that equalizer sign, let's go and look it up really quick. Triple equal in Swift. Because I cannot remember if it's a class indicator or if it's an instance indicator. Hacking with Swift. Okay. Swift gives us 2 equal operators. The double equal sign and the triple equal sign, and they do slightly different things. You will almost certainly need to use both of them, so it's worth taking the time to learn them. Okay, we already know what the first one is, so let's go to the third one. In comparison, the triple equal is the identity operator, which checks whether 2 instances of a class point to the same memory. Yes, okay. So this goes back to the difference between reference types and what is it? Fuck, man, I can't remember what the other reference types. Obviously, is you're referencing a point in memory. What is the other type called? Give me a second, guys. He says the first line I read is a racial line, and I read the news. Oh, chemo. The first that are you talking about the video? That was a video I posted like a day ago though. But anyways, back to what I was saying. So there's two types of items that we work with when we're writing code in Swift. As far as storages of values, there's classes. Classes are reference types, which means that they point to a specific reference, a pointer in memory. And then you have structs. Structs are basically just built on the stack. They're copies of each other. They're not in the memory heap. I'm trying to remember the actual proper terminology here for the difference between reference types and, oh, it's on the tip of my fucking tongue. I'm really not that worried about being able to use the exact terminology because in a job interview, if they ask you what the difference is, I can describe what the difference is. And I'm pretty sure that's enough to let them know that I have a decent understanding of the difference between the two things. I just don't remember the proper terminology. Let's see if I can find it here just to give myself a refresher. Value and reference types, that's what it is. So obviously classes are reference types, structs are value types, right? Structures, enumerations, tuples are all value types. Okay. And I might have to go and do a little bit of refreshing on, oh, what is the exact, other than the two memory management systems, what are the other differences between structs and classes? But at the same time, I'm applying for a senior position, so I don't know if they're really going to ask me those kind of stupid questions. He says, did get a daughter. Are you a dad yet, or your girlfriend have a baby yet, bro? Yes, she had the baby 2 days ago, Abdul. Thank you for asking, man. Okay. Yeah, it's okay, baby. You can put her like right here. Let me just... Okay, so let's watch this video with the AVL tree. Octavia, why are you sideways? He loves going sideways. So we're going to watch an AVL tree Swift video. I'm kind of worried about watching this just because we already learned a way to do the binary trees and I don't want to get confused, right? Because the problem with programming, and a lot of people don't seem to understand this if they've never programmed before, is there are like many ways to do the same thing on any given task when you're programming. The other thing is they call this an AVL tree, but this is still just a normal binary tree. I mean, this is still a binary tree. Balanced, unbalanced. Now, I don't remember the difference between balanced. Well, I do know what it means. Balanced is when it's an even number of leaves. Unbalanced is when it just goes in one direction. So let's watch this video and let's see. I don't know what programming language it's going to be in though.
An AVL tree is a self-balancing binary search tree that automatically maintains its balance to ensure that operations remain efficient. To understand how AVL trees maintain their balance, we first need to introduce the concept of the balance factor. The balance factor of a node is the difference between the heights of its left and right subtrees. Let's take a closer look at this with an example. Suppose we have a tree where the root node has 2 children. The balance factor of the root node in this tree is 0, because the heights of both its left and right subtrees are the same. In this case, the node is balanced. Now consider the left child of the root. The left subtree is taller by 1 level compared to the right subtree. That means the balance factor is 1. This node is also balanced. Next, let's examine the right child of the root. The right subtree is taller than the left subtree by 1 level, so the balance factor is -1. This node is also balanced. However, problems arise when the absolute value of the balance factor of any node becomes greater than 1. In other words, if the balance factor is either more than 1 or less than -1, the node becomes unbalanced. When this happens, the AVL tree performs rotations to restore balance. Before we dive into...
Oh no. Okay, so see, this is the one thing I hate this. This is why I don't like binary trees, because it's like layers of complexity, right? Layers of complexity. The first thing is that the tree itself, doing it, is complicated. Insert, deleting, recurring through the tree is a little complicated. But now on top of that, we need to add a balancing factor, right? Which can become... let me not make the mental roadblock before we get into it, because my memory is telling me it's difficult, but maybe it's not. You know, I've been doing this for long enough to realize now that maybe it's not that difficult. Now on his node, and you know what? Let's create a new playground. We already did the binary tree, the generic binary tree. Let's rewrite the binary tree one more time, but this time we're gonna make it a AVL, auto balancing binary tree. So let's close this. Let's open a new one. New playground. Yeah. I know, I see that. He always gets out of it. I don't know how. AVL 3. Okay, so we got the AVL tree. That's all. Give me a second. She's doing okay, baby. I'm just getting these cables out of the way so they're not like hanging over. He's about to turn into a cyborg baby. He's about to turn into a cyborg baby. This chair, I can move it out and put it all over here. Or let me just move it. No, I can do it. Okay, guys. Let me rewrite. Let me rewrite the node first, right? So we're going to be writing the node from scratch again. So class node, and then we're going to add a var value, which is just going to be an integer for now. Integer. Var left, which is going to be a node. Var right, which is going to be a node, optional. Var balance, which is going to be an integer. And I think it's supposed to start on 1. And then we're going to make a class AVL tree. Yeah, just let's call it AVL tree. AVL tree, this is going to have a root. Var root, which is a node optional. And then it's going to have some functions on it. Class node has no initializers. This is because it's a class, so we need to add the initializers in it. We're just going to add the value one. Value. We don't need to actually make it say value. Value integer self dot value equals value. Okay, so now we have the node, we have the class. Now I am trying to recall, and we can open both playgrounds actually. I'm trying to recall when we're doing the insert, how do we check, right? How do we check the value of the balance? I think what we do is that when we add an item to one of the sides, right, root.left, we add a value to it, then we subtract from the count, right? We subtract from the count. So each time we add one, and this is just me talking through it, I don't really know if this is the way to do it. I don't remember. I don't even remember if when I was learning how to do this the first time, if I even bothered learning AVL trees. And I think I honestly didn't because it was just unnecessarily complicated. But I think that what we need to do is that when we insert a value on the tree, right? When we insert a value on the tree, we are going to check the balance variable. And every time we insert a value, we're going to subtract from this this variable. And when it goes to 0, I believe, or -1, if it goes to -1, then we have to rebalance the tree. And rebalancing the tree, I don't remember what it consists of. I think it's just moving the nodes over so that the nodes are back in sync. So there's only one level of difference between each one. But we'll see.
Rotation.
Like I said, I don't remember.
Let's first go over the code for the node and tree structure in an AVL tree. In the node class,
also, I don't know what language this is that he's showing us this in.
This value is stored in a member called value. Just like in a regular binary search tree, there are also left and right members that point to the node's left and right subtrees. What's unique about the AVL tree is the height attribute. This attribute keeps track of the height of the node, and it's crucial for maintaining the tree's balance. Unlike a normal binary search tree, where we don't worry about balance directly, the AVL tree uses this height to ensure that the tree stays balanced at all times. In the AVL tree class, we'll start by defining the root of the tree, which is initially set to none. Next, we'll define two important methods, height and getBalanceFactor. The height method is straightforward. It simply returns the height of a given node. The algorithm first checks if the node is none. If it is, it returns 0, indicating that a non-existent node.
Okay, so I don't know what language this is, but like I've told you guys in the past, it doesn't even matter. So instead of doing this all from scratch, let's try and cheat here. Let's add this variable to the other playground we had. You know, you know what? Let's not do that. Let's just do it here. Let's not be lazy. Func get height for node, right? And this is going to be return. Now the question is, does it return root dot balance or height, whatever you want to call it? This is going to return an optional integer. Actually, it's going to return an integer. It doesn't even mean optional. Let's just guard let balance equal root dot balance, else return 0, I guess, right? And then here we can just do balance. I'm trying to think though, what am I trying to do with this? So the question is, when they're going through this, is it taking this value for the entire? No, it's taking it for the node that's passed in. So let's do something different here. Let's add node, not optional. And we'll do node instead of root. So it's not going to grab it from the original root. It's going to be grabbing this from, and then let's make it optional. Fuck it. It's going to be grabbing it from whatever node is passed in. Let's get height for node. And then the other function that he has is func get, what does he have? Get balance factor. Get height factor, we can just call it. Let's just make it a closed function. Do this. And then let's see what he does here. So he checks to see if the node is nil. If node is nil, return 0. And if not, return. Okay. So, and he's passing in a node. He is passing in a node. Node. We'll just make this one not optional, right? For now. This is going to also return an integer, right? From what I can tell, right? Define height, get balance. I don't know what language this is, but it doesn't have a return type, but I can see he's returning a value. So it is definitely returning a value. I just don't see it defined. Anybody know what language this is? I honestly don't know what language it is. So he does guard let node equal node dot balance, right? Let's see. No, he just returning node, so not even that. It's just node. It's just node. Else return 0. Is the pump working, baby? This can be optional because his was optional. And then he does return node dot left dot balance minus node dot right dot balance. Actually, I'm wrong. He didn't do that. He did this. Get height factor for node dot left minus get height factor node dot right That's what he did. Left minus right. Okay, yeah.
Has a height of 0. Otherwise, it returns the actual height of the node. The getBalanceFactor method works similarly. It checks if the node is none, and if so, it returns 0. Otherwise, it calculates the balance factor by taking the difference in height between the node's left and right subtrees. These methods are crucial as they help determine if the tree needs to be rebalanced. In addition to these, we'll also have other methods like insertion and deletion, which we'll discuss later.
Okay, so another challenge for me would be to rewrite the insert, right? Rewrite the insert method. So let's fucking do it. Let's fucking do it. See if I can remember how to do this. Func insert. And this is going to be taking in a node. And then I'm going to do it the way that they showed me how to do it in that other tutorial, right? Insert helper, which to me seems more sensible, right? Makes it more simple to do. So here we're going to insert the node. So we're going to say guard let first node or root node, you know what, first node equal root node, else we don't need to do the space below, else return. Actually, I'm a little wrong here. It's not else return. It would be if root is nil, then we're going to say root equals node. There. Now, if root is not nil, we're going to say this takes in a node as well. Node. And it takes in a optional root, or let's just call it something more sensible, parent node. And we're going to make this a node as well, optional, right? And I reversed the order of the parameters, but it's fine because I don't want to memorize the steps. I want to memorize what actually is happening, like the logic behind what's happening. So now we're going to go ahead and pass in. So this is going to be return, doesn't need to return, it's insert helper. It's going to be the node that we're passing in, and it's going to be first node there, right? So then now under the insert helper, we're going to make sure that the parent node is not nil. We can do it with an if statement. It'll be easier to understand what's going on. So if parent node if let node, let's do if let node equals parent node, else return, and we're going to return node, right? And I'm trying to remember when we're inserting nodes, this returns a node as well, I believe, if I'm not mistaken. Unexpected else. Sorry. Let's change this to a guard. Okay. And return node. That returns node. And then in here, this can be discardable, right? Discardable, because we don't need it every single time. And we can just return a node here as well. I don't think it's needed, but we can do it either way. We can just go return in here. Return root. Okay. So that should be fine. So now over here, we already looked at the parent node to see if the parent node is nil. If the parent node is nil, then we're just going to assign that to the node in question. So now in here, we need to do something like if node dot, let's see. If node dot value is less than parent node dot value, else. Right? And we're gonna do if it is first of all, we know that this node these cannot have the same name. So let's change the name here. This is gonna be parent node still. Okay, and then this is gonna be this, because we cannot have them have the same name. Okay, so then in here we're gonna do if node.value is less than parent node, then it needs to go to the left, right? Because the parent node is up here. We're trying to add a new value. We're gonna add it to the left. So we're gonna say parent node dot left equals insert helper, and we're just gonna go down the chain again, and we're gonna say the node, which is the node that's getting passed in node, and we're gonna do parent node dot left, and then on the other side we're gonna do the same thing. We're gonna do, instead of it being left, you know what? Let me not be lazy. Let me type it out. Parent node dot right equals insert helper, and then this is gonna be the node, and it's gonna be parent node dot right. Right? Does this make sense? And then this is gonna return parent node, not node. So I think that this is the same logic we had before. And we can test this out, I guess. But I can also just look at the other playground and see how we did it over there and see if we did this the right way, which is probably the fastest, easiest way to do this. So let us do that instead, because I'm lazy. So yeah, here we did exactly the same thing, right? Base node is the first node, root, we did that. Now we changed the order of these two things, but it's still the same thing. We checked to see if this is this, and it returned the node that we were passing in, yes. And then we did if less than, we did parent node, which is the root, left, insert, and we did the same thing here. We did the same thing there. That was fine. So now there's an additional element to this that we need. And the additional element is the balance. The cat is freaking out. Are you guys seeing this? Winter. Are you guys seeing this? The cat is looking at our child in the bassinet. You better not jump in that bassinet. Are you guys seeing this, chat? Are y'all seeing this shit? This damn cat. Are y'all niggas seeing this shit? Nah, Winter's wildin'. Look at this. Zoom in. She's wildin', chat. Yo, why you eyeing my daughter like that? Yo, this cat is weird. It's bugging. Y'all, yeah, yo, chat, let me know if that cat tries to do anything crazy, man. Cat's making me nervous. He making me nervous, I'm not gonna lie. But anyways, back to what I was saying. There's an additional element now being added to this. The other thing is, remember that when we pass in each one of these, we're checking to see if the value is nil, which means that we don't even need this logic here, I don't think, because let's think. If first node equals root and root is nil, that means there's going to be no values, right? Which means that it should return node. So we really don't need to do this like how we did it. We could just do return. We can remove this and we can do insert helper. We can do node, the node we're passing in, and we can do root like that. And this should give us the same result. And we can test this out on the other playground. We can test this out on the other playground by doing the exact same thing, just removing this. Right? Boom. Pasting that here. Boom. Changing base node to root, which is going to be nil. And then changing nothing else. We can erase this. Boom. Can erase this. Boom. And now when I run this, it should do the exact same thing because we passed in the root. The root is nil. Okay, there's one thing that's missing though. If root is nil and we do this like this, when we run it, nothing's going to happen because it's in a vacuum. So we need to do root equals this. And then this needs to be return root like that. And now everything should be the same. See? And we can just do the same thing here since we already know what we're trying to do. So root equals, and then return root. Now I feel like there's another shortcut we could take here. Instead of checking each one of these, first of all, this doesn't even need to be done like this. I like this method more because I think it is cleaner than if we had a while loop here and we were just going through a while loop recursion. It's easier to read in my opinion, but I could be wrong. Or it's up to your preference, right? Anyways, let's get back to the insert method and let's see what they do here for their insert method. I don't know why I thought that this was so complicated originally. It's really not that complicated. And the recurse is also not that complicated. This recurse is basically just passing in the root and then just looping through it. And if it's nil, it will stop because both methods only get called when the item we're trying to access is not nil. But anyways, let's see what they do. Let's see what they do.
Methods will rely on the height and balance factor to ensure the tree remains balanced after every operation. Now, coming back to rotations, there are a total of 4 ways a node can become unbalanced, depending on its balance factor and the balance factor of its child. The first case we'll look at is the left-left LL case. This occurs when the balance factor of the unbalanced node is greater than 1, meaning it's left-heavy, and the balance factor of its left child is greater than or equal to 0. In this tree example, the balance factor of the root node is 2, which means the node is unbalanced on the left side. The balance factor of its left child is 1, indicating that this is a left-left case. To balance the tree in this scenario, we need to perform a right rotation on the unbalanced node. After rotating, the left child becomes the new root node, and the original root moves down to become the right child of the new root. This rotation effectively redistributes the nodes, making the tree more balanced. Now, the balance factor of the new root node is 0, indicating that the tree has been successfully balanced. Now, let's go back and add a right grandchild to see the general left-left case in action, along with the code. Initially, the balance factor of the root node is still 2, indicating that it's left-heavy. The balance factor of its left child is now 0, which means this is still a left-left LL case, but in a more general form. Let's break down the code for this rotation. The method takes a node as input. Here, we'll use the root node, which we'll call Z. Next, we set Y to the left child of Z, and T3 is set to the right child of Y. In the previous example, this T3 was none. Now, we proceed with the right rotation. The right child...
Okay, so here's the logic for this rotation. The names that this guy gave these nodes is stupid. So let's see if we can understand what he did. I don't know what language this is he's writing in. If you guys have not noticed the trend, there really aren't that many great, amazing videos on Swift, binary, data structures and algorithms in general. It's always in some funky language like Java or Python or JavaScript. I don't know what language this is, but let's do the translation. So he made a new function called rotate right. And this new function, does it take in any parameters or any arguments? Let's see. It has a parameter of Z. Z, I don't know what Z would be. Is Z just the root? I mean, it's currently the root. I don't know if it's the root right now. Let's just say rotate right root. I don't know. And this is going to be a node because it's unclear to me what name, what the naming convention, right? Let's not call it root. Let's call it parent node. Because if we call it root, then we're not going to be able to use the root property that's on the AVL tree itself. So then he has the right and the left of the child, right? So what's interesting is in this language that they're using, they don't need to define the values, I don't think. So let's just put left and right, var left. Why did it autocomplete? Var left equals parent node dot left, var right equals, and actually we already know that this is going to be left dot left, or left dot right. And what they're doing here, I see what he's doing. He's saving he's saving the variables, right? So he knows that it's left leaning. When it's left leaning, we got to rotate right. So then he's going down that tree. What happened? Did you get a lot though? So he knows that he's gonna be grabbing the left items. So he's storing the value of the left nodes further right value, right? So left, let's just call this one left right. He's just trying to save the reference to it. And then and then now he's going to rearrange them. So he has, what is it? The Z height, which is going to be parent node. Can we just call it parent node height? Which is parent node dot. This is interesting. I don't know what he's doing. Z equals height equals 1 plus max height dot Z left. Self height Z right. Let me hear the explanation. Part of it is I don't understand the language that he's using. I don't know if these cannot possibly be pre-existing variables. So I guess in this language you can just define variables on the high. Max. I don't know. 1 plus max self height Z left. Self dot height dot right. Yo, thank you for subscribing, dude.
Of Y is assigned to Z, and T3 becomes the left child of Z. This rearranges the nodes, effectively rotating them to the right. After the rotation, we update the heights of Z and Y to reflect the new structure.
So let's skip this part. I didn't even notice that he had done that before. So he saves a reference to the Y right, which is this one. Then he goes to Y dot right, which is left dot right, right? Which he already saved. You know, he saved the reference to it. And he makes this. What did he make this? He makes this the current parent. So parent node. And then Z dot left, which is just left, he makes that parent node dot left. He makes that the left right. He says computer science. Yes, I'm just trying to practice AVL trees, Alessandro. So let's see if we understand what's going on here. And then what does he return? He returns Y, which is just left. The naming convention sucked. And then, oh yeah, I mean, so you are giving some, yeah. What's that do? I studied computer science in high school. Now I go to university first year. I'm 19. You're in America, Alessandro? If you're in America and you're studying computer science, I would say to drop out and just go try and find the job. I'm Italian because the market is way oversaturated. You're Italian. Are you studying in Italy or are you studying abroad? Okay, so here he has the rotate right. He passed in a parent node. He saves a reference to the left branch of the current parent that they passed in. Left, right. He saves a reference to the furthest right node of the left tree, right? Left dot right. He makes the left dot right, right? The parent node. So let's think about this. Let's think about this. The parent node is now going to be left dot right, which is larger than what it was before, but I need to see this in a diagram. And then parent node dot left. He makes parent node dot left. Left, right. And then he returns left. And then he rebalances everything. I would have to see how you do this in Swift, the rebalancing, because this is definitely not Swift. He says, which language is JavaScript? This is Swift. I don't know what language he's using here. I don't know what language he's using here. So let's think about this before we do the rebalancing, because even the rebalancing that he did, I don't fully understand. So we have the parent node. Let's say the parent node is 5, right? 5 has 2. It has 2 nodes. It has 2 nodes on its left leaf. It has 2 and it has 1. The 2 has a number 3 on its right node. So he grabs the 2 and he saves it, right? On the left property. He grabs the 3 and he saves it on left right, right? Now, the node 2, he makes equal to parent node, left, right. He makes equal to parent node. Boom. And then parent node left, he makes it left, right. I need to write this down. He says exactly, Chimo. Oh my God. That you guys are responding to like an old ass message from like, I don't know how long ago, an hour ago. Damn, let me play this back again because that was kind of confusing. I'm not gonna lie. Well, that's good, baby. How long does that last?
To become the right child of the new root. This rotation effectively redistributes the nodes, making the tree more balanced. Now, the balance factor can become unbalanced, depending on its balance factor and the balance factor of its child. The first case...
Yeah, I need to find a better explanation of this because I hate AVL trees. I'm not gonna lie.
...is the left-left LL case. This occurs when the balance factor of the unbalanced node is greater than 1, meaning it's left-heavy, and the balance factor of its left child is greater than or equal to 0. In this tree example, the balance factor of the root node is 2, which means the node is unbalanced on the left side. The balance factor of its left child is 1, indicating that this is a left-left case. To balance the tree in this scenario, we need to perform a right rotation on the unbalanced node.
Okay. So let's think through this logically, right? Because sometimes you got to forget about the code and you just got to think about it logically. You have 10. Yeah. He's just sleeping, baby. Winter almost jumped in there. If you go on my stream and you scroll back, you'll see I got Winter almost jumping in there. From there. Yes. Wait, look. I'll pull it up on my phone. By the way, these coding streams get a lot of subscribers, bro. Jesus. I'm talking to the chat, baby. Sorry. Here. I'll show you. I'll pull it up. I was like, what the hell is she trying to do? I'm trying to. Sorry, guys. I'm just trying to find something for Bailey. Yeah, she's. I'm a little slow, guys. Mentally. It just happened like maybe 15 minutes ago. Like she literally is gonna jump in there. Like I'll show you. Here. Look. Easy. But if you go back a little more, she was like crouching over. Okay, so in this example, we're doing a right rotation, right? You've got 10, 5, 3, and we want to bring the 10 down. So we're gonna rotate to the right, and we're gonna make it 5, 3, 10. This one's simple. When it's just a straight line like this, it's actually, I think it's simple. If we think through it in code, how would we do this? Let's think. Right rotation. Let's grab the code. So we have, well, this is right rotation right here, right? So we have the 10 that we passed in, right? And we want to save a reference to its leftmost item. So it's going to be the parent node left. Left dot right is going to be, what is that? Left dot right is a new variable that we're just creating out of tin cloth. This should not be left dot right. It's going to be new right. Right? New right. Let's give it names that describe what it does so we can understand the algorithm better, because the way this idiot explained it, did not, it doesn't clarify it right. And this is actually not a good name either. This should be left child old right, something like that, so we can understand what the hell it is. Okay, so if we go back to the example, we have 10, 5, 3. We saved a reference to 5, which is going to be left. There is no value on 5 to the right, so this is going to be nil. Left child old right is nil. Left dot right, we're going to make it the parent node. So left, this is this item right here, right leaf. We're going to make it the parent node, which was originally 10. We're going to move the 10 down, right? And then parent node dot left is going to be the left right's child. So we know that the value that was here before that we stored, even though this time it's nil, but the value that was here before is going to be, okay, going to be less than the 10. So now we know that 10's left value is going to be the old left's right value. So left child's old right is going to now be the parent node's, it's going to be the parent node's left item because it's less than the new parent node. We changed the value, and then we're going to return left. and left was parent node left. So we're returning 5. And 5 is just gonna have the new updated tree. So I think that the problem is you can't even really look at these values and try and figure it out that way. It's just you gotta conceptualize it before you even start to like write out the algorithm. That being said, now you need to do the math to add the new node count. And I feel like doing this algorithm that he has here, get height for this and get height for that, and subtracting them, I think there's a way to do it where you don't need to do the math yourself. But I'm not sure.
After rotating, the left child becomes the new root node, and the original root moves down to become the right child of the new root. This rotation effectively redistributes the nodes, making the tree more balanced. Now, the balance factor of the new root node is 0, indicating that the tree has been successfully balanced. Now, let's go back and add a right grandchild to see the general left-left case in action, along with the code. Initially, the balance factor of the root node is still 2, indicating that it's left-heavy. The balance factor of its left child is now 0, which means this is still a left-left LL case, but in a more general form. Let's break down the code for this rotation. The method takes a node.
So then now, the part that I kind of got a little confused by is his new calculation for the heights. So there's going to be down here, left dot height. It's going to be left dot balance. I called it balance equals, and we're going to have parent node dot balance equals, right? Because those are the two items that changed. Z was the parent node, Y was the previous left node. And then we have 1 plus. He just did 1 plus. And then he has max self dot height. Okay. So I don't know. Returns the greater of two comparable values. I'm assuming this is the same thing between both languages. So we're just gonna do when he does self height. Oh, this is because he's calling the function, right? He's just calling the function. I'm assuming I can just do get height factor, and here get height factor, right? And then it's just gonna be left dot left dot right. And then the same thing is going to be done for the second item here. Boom, boom. But instead of it being left, it's going to be parent node. Parent node. Parent node. Like this. And I think that this is the equivalent of what he did in his example. And I think his method for get height factor, because he has two different methods. Let's go back to when he was defining the methods. So height. So it's not this method that we want, it's the other one. Get height for node. What was the difference between these? This one was just a comparison. So it's subtracting the left from the right. But this is actually getting the values of the left and the right. What is that you have in your hand, my love? Because I'm hungry too. I'm hungry and I'm sleepy. And I don't know if I'm really grasping even what I'm doing because I'm so tired. But I think, guys, you know, we did right rotation. I don't know if I want to actually look at somebody's algorithms to figure out how to do this. I think that I should be able to figure this out by just looking at the nodes and analyzing what I want to happen. This at first was confusing, but now I'm seeing that no, it shouldn't be confusing because we created a new item left. We recalculated it by just grabbing left and right. And then here is just parent left and right and adding one. Really not that crazy. It really isn't that crazy. It really isn't that great. It looked crazy because I don't know what language this is that he's writing this in, but it really is pretty self-explanatory once you kind of look. And then when the question is, when do you remember when you're doing a right rotation, a left rotation? Obviously a left rotation I would assume is if it's left heavy, right? No, I'm sorry. I would assume if it was right heavy. So if it's right heavy, you do a left rotation. If it's left heavy, you do a right rotation.
Node as input. Here, we'll use the root node, which we'll call...
This can get very complicated, though.
Next, we set y to the left child of z, and t3 is set to the right child of y. In the previous example, this t3 was none. Now, we proceed with the right rotation. The right child of y is assigned to z, and t3 becomes the left child of z. This rearranges the nodes, effectively rotating them to the right. After the rotation, we update the heights of z and y.
They have the axis and stuff. It'd have been nice if they brought us food. AVL beggars can't. But it would be nice. Okay, I'll wait until they get here and then I'll end what I'm doing. So at least can see what I'm doing. Serious. Watching Kaisen at. This is complicated though. I mean, I think I'm understanding it, but at the same time, I'm like, oh. Because I don't remember the patterns. Right, Winter? Don't remember the patterns. But I also don't think in a job interview, they're going to ask you to use a fucking AVL tree because it's kind of too complicated. Like, why would they? They might. I mean, if they're crazy. If it's like Google or some shit or Facebook, then maybe. Because those companies pay way more. They want to make sure you're not a dummy. But a normal job like the one I had before, they never asked us any of this kind of shit. They asked me like a very simple question. They asked me like a very simple question, and then they were like, oh, go make a project at home and bring it back. Oh, yeah, here they are. Oh, now you want attention. Winter, your time is done. Is the house clean? Tell her when he gets here, it's normally not like this, but I mean, we got a lot of shit going. We got a lot of shit going on. Your boyfriend has no job. You just got a baby. Okay. Oh, okay. My nose is getting pointier. Yeah, because before it was like completely flat. I was like, oh no, I hope my baby doesn't have an ugly flat nose. Either that or I'm just getting used to seeing it. I gotta go back and look at the old picture. Anyways, guys, we're gonna be wrapping this up, and then I guess tomorrow I'm gonna have to finish this AVL. Today I didn't apply for any jobs, by the way. Did I? Yesterday I applied to a whole bunch. I gotta go through all my emails, and I need to delete all of the confirmation emails that you get when you apply to the different jobs. And then I need to sit down and I need to think about these AVL trees and not think about the code. You know, the problem that you have a lot of times when you're a software engineer, especially when you have no experience, even though I do have experience at this point, so I don't need to do it that way anymore, is in the beginning, when I first learned binary trees and AVL trees, I was memorizing, like I was doing it like when you do math, right? When you do math, you memorize the steps. And a lot of the times you can know how to do the math. Like they'll say like, oh, find the cosine of this angle or whatever. Find the sine of this angle. Find the tangent of this angle. Find this, find that. In trig or in algebra, they'll be like, use the quadratic equation to break down this quadratic equation, I guess. I don't know how you would say it. But you memorize the steps and you're able to figure out how to do it. But with programming, yes, you can memorize the steps and you can get through it, but it's better to actually understand what you're trying to actually do. And in the case of the binary tree rearranging, the yeah, no, it's all right, baby. I'll bring her over when your parents come out. I'll take her out of. I'll push. The thing is that you need to understand what you're trying to actually do, because at the end of the day, you're not trying to memorize steps. You're not doing math. We're not doing math here. We're trying to get a result. And when I say a result, I mean like a tangible physical result. So you should be able to look at the tree or look at the problem that you're trying to solve and walk your way through the problem. And in the case of balancing a tree, I should be able, first of all, to loop through the tree. I should be able to look at the tree and say, how do I want to loop through this tree? What steps do I need to take to loop through this tree? She's a little slow. She's looking at her paws, I think, but I don't know why. I don't think so. I don't see anything running around. Winter. Is it? Let me see. Are you sure? Did you see it? Can you see it? Let me look. Go to the elevator. Are they in the elevator or on the outside of it? Okay. It's 2. It's only 2. We should have taken it. We should have been sleeping this. I know, and I wanted to study a little. I didn't do it. Up there. Playing that video games. And I'm not gonna lie. Like I'm not gonna lie. Like me doing this right now, I think I did kind of get a little bit of understanding of what it is, except that I don't know. I still got to think about the balancing aspect of it. But I think once I get the balancing aspect of it understood, then I'll be able to just write the algorithm out myself without having to look at even an example of it, which is the goal, right? The goal isn't, like I was saying, it's not to memorize how to do it. It's to understand what you're trying to do and then write the steps needed to do it. That's what it is. It was like a little spotted beetle. I've never seen it before. It was like black and it had like red spots on it. Yo, Rob, thank you for joining, bro. I'm about to end. I was just doing like a little bit of a recap here of the binary tree, and then I was going through AVL trees. We were watching this video. I don't know what language this guy's writing this in, but we were just translating it over to Swift and trying to just understand the underlying concepts of what he's doing. And I was able to write it out in Swift and think through it. And I think I got it. I think I got it. They're going to be here any second now. Let me go to the door. No. Anyways, guys, I hope you guys learned something today. I'm going to go ahead and end the stream, even though I wanted to prove a point that I'm like working. So I'll catch you guys later, man. I might do an hour in the night. Catch y'all later. Peace. And oh, by the way, if you guys are trying to learn this, I hope it's helping the people that are trying to actually like figure it out, even though I don't know why you'd want to do that, because, you know, we're all getting fired at the end of the day anyway.